Hello, this is Dean Atkinson. I'm presenting the fluorescence quenching determination of chloride and bromide lab. That's in our inorganic, our anions pair for our Chemistry 427 instrumental analysis lab here at Portland State University. So the assay in this case will be the simultaneous assay for chloride and bromide in a solid. So one of the challenge samples in this case will be a solid sample that contains both chloride and bromide, a couple of different salts. Solution phase samples will be made from that, and then the solution phase concentrations will be determined. You'll work your way back to the assay for the solid, the ions in the solid, which makes kind of a nice tie-up to the end is, you know, how well can you determine the solution phase concentrations and how well can you work your way backwards to a solid phase concentration or a solid phase composition. The summary here, we're using fluorescence spectroscopy. So fluorescence spectroscopy I'll say a few words about. In the quenching mode, so I'll distinguish between fluorescence spectroscopy used directly to determine things and in this indirect quenching mode to determine things, in this case the anions, the chloride and the bromide, in that solid challenge sample that I just mentioned. The method of quantitation in this case is going to be a direct calibration. So you're going to use standards that you create. In this case, it's going to turn out that you need to make a set of different standards, and the actual solution for the chloride and bromide, similar to what's done in the pH lab, will actually come from the solution of two simultaneous linear equations. And so as with the pH lab, there will be a number of pieces of data that you'll have to collect from the calibration experiments before you, well, in principle, before you solve for the unknown concentrations, and then you work your way back to the unknown composition of the solid. In this case, you have the opportunity to actually say something about the uncertainty because you can do replicate analyses, and I will point out towards the end that that's a little bit challenging because of the nature of the two equation solution. So, I'll start again with fluorescence spectroscopy. So this is a couple of cartoons that are generally used to describe fluorescence spectroscopy. Fluorescence spectroscopy, of course, is when you put a photon into a molecule and get a photon back out. And so I've diagrammed here the absorption experiment, which takes a molecule from the ground state to the excited state. These are molecules, and so one set of labels that is often used in, for instance, in organic chemistry and a couple of other places to describe these states is these labels. So this would imply that this is a singlet ground state and the singlet excited state, which is generally true. Singlet means all the electrons in the molecule are paired, and that's generally true for things like organic molecules. And so we're talking about an excitation from two states, from one state to another state that is of the same overall spin symmetry, and so that type of transition is strongly allowed. Of course, the fluorescence experiment is not diagrammed here because the fluorescence experiment would be when you come back down from the excited state to the ground state, and so the photon that you actually get out is the one I just drew in there. So you can excite molecules from the ground state to the excited state, but you don't get fluorescence until they fall from the excited state back down to the ground state. The beauty of that experiment from an analytical chemist perspective, so again, you know, there's a couple of different types of diagrams on this figure, and the thing at the bottom is to remind you that the stuff on the right-hand side tends to be how the analytical chemists think about fluorescence spectroscopy, and the left-hand side is sort of how physical chemists think about it, although there's quite a lot of convergence in between. Because a lot of analytical chemists tend to think about the physical chemistry side of the story as well. But from the analytical perspective, this is both a good and a bad experiment. The reason that it's both good and bad has to do with this cartoon over on the right-hand side, the analytical chemist's version. So imagine that we took a source and we shown it on the sample, which is contained in the cuvette here. The light that's created by first the excitation from the ground state to the excited state, and then from the excited state coming back down to the ground state. So again, this photon that's coming out, that's the black arrow that I've drawn here, it has no preference in terms of direction. It can go in all 4 pi steradians of space. It can go out any direction along this plane and in any direction that comes out of that plane, up, down, back, forth, whatever. And so what that means is we're not apt to catch all of the photons. Because we can't steer photons, we're probably only going to be able to detect photons that hit our detector. So that's a bit of a bad thing. Means we're not going to detect all of the photons that are created as a result of this process. But really, it's a very, very good thing because it means that we can put the detector anywhere we want. And so there's sort of an infinite number of possibilities. We can put the detector here. We can put the detector here. We can put the detector above or below. We can even put the detector back where the source is or over here on the other side. It turns out there's only two wrong answers. Putting the detector where the source is a bit of a problem because they share the same space. Putting the detector on the other side of the sample is really the worst possible place to put it, and that's exactly where we would put it for an absorption spectrophotometer. So in an absorption experiment, we need to look at the light that comes from the source, goes through the sample, and makes it to the detector. Because what we're looking for is a decrease in the intensity of light that shows up at the detector. In this experiment, we do not want to see light that came from the source. And so the most logical place to put the detector is at a 90-degree angle to the source light, because that means that most of the source light is going to pass through the cuvette, come over here and strike some kind of a beam dump that's going to keep the light from following this path down this way and striking the detector. So one of the really good things about this experiment is we really, in general, will only see light that's created as a result of this event. We shouldn't see light that came from the source and made its way to the detector. So the only light we should see is as a result of this fluorescent event. The thing that strengthens that argument is the rest of the cartoon over here. So because this is a molecule rather than an atom, there's not just one distinct electronic ground state and one distinct electronic excited state, excuse me. In fact, there are a whole bunch of vibrational states associated with the ground electronic state, and likewise there are a whole bunch of vibrational and rotational states associated with the excited electronic state. So when we go from the ground state to the excited state, there's multiple possibilities. So one of them is the first arrow that I sketched, but there are also arrows that go from the ground state to a higher level of the excited state. And keep in mind that I've only drawn the electronic states here and the vibrational manifold coming off of the electronic states, but in principle, every one of those electronic states spawns a whole range of rotational states. So there's really almost a continuum of states in this region and a continuum of states in this region that you can be exciting from and to. One point being, though, that all of these photons start here and go up to various levels up here. So all of these photons are bigger than the original photon that I drew. And the other possibility for the downs involves coming out of this bottom state here and going to states down here in this region. So I'm going to draw one of them here. And by and large, all of these photons that I've drawn here are going to be smaller than the original photon that I drew. So I didn't do a very good job of drawing that photon. It's supposed to originate on the bottom excited state here and go to states down below. Now you might say, to yourself, well, if you went from this ground state to this excited state, how come you can't come back out of this excited state and come back down, let's say, to this ground state, which would be a photon that's almost as big as the photon that you started with? And the answer is, when you put photons into the system and create these excited vibrational and rotational states up here in the electronically excited state, they very rapidly interconvert back down to this lowest level that we drew for the excited state, the electronically excited state. And there's a pretty good rationale for that. This is a solution phase sample. These are fairly complicated molecules, and in a solution phase sample, all of the molecules are basically shoulder to shoulder. They're all touching one another, and so if you try and put rotational or vibrational excitation into the system, that rotational or vibrational excitation can be rapidly transferred to the molecules that are on either side of that molecule, either solvent molecules or molecules of the type that you're talking about. And so all of those transfers take place extremely rapidly, on the order of picoseconds or maybe even femtoseconds. And so within a very, very short period of time, any excitation that you put into the molecule is driven away or is sucked away, and you end up down in this lowest possible state, this lowest possible vibration and rotational state of the electronically excited state. But then you can still fall down into all of these lower states that are all different vibrational rotational combinations originating from the ground electronic state. So the electronic transition takes place for sure, but how much of the rotations and vibrations take place it has to do with whether you're in the excited state or in the ground state, because the excited state transitions, the excited state energy gets coupled away very rapidly. The upshot of all of that is that the photon that goes in is almost always bigger than the photon that comes out. And so what I've sketched down here is sort of an artist's conception of what those spectra look like. So the excitation spectrum is all the different wavelengths of light that can be used to promote the molecule from its ground state to its excited state. And typically, you know, some of them are better than others. Some of them have higher population than others. Some of them have higher line strengths than others. If you don't know those words, don't worry about it too much, but you are a senior in chemistry, so we sort of assume you've heard those terms before. So there are a variety of different transitions that are involved in taking the molecule from the ground state to the excited state. This is basically the absorption spectrum of the molecule. If you wanted to record that as an absorption spectrum, you know, of course you could record it in absorption, but you can also just fix the emission wavelength and scan the excitation wavelength, and you would get a spectrum of this nature. The other thing you can do is park yourself on any one of these emission excitation features and scan the emission spectrum, meaning you look at all the different wavelengths of light that come out of the molecule when you excite at that wavelength. And again, you know, you see this sort of distribution of different energies or wavelengths involved, and all of those basically all those different transitions from the lowest state here down onto these states down here on the lower electronic state, on the electronic ground state, manifest themselves in that spectrum. So there's two different types of spectra that you can take, one that looks like an absorption spectrum, one that we term an emission spectrum. In principle, you can measure both of those at the same time. That's a fairly complicated experiment that people don't always do. If you're interested in just measuring stuff, though, you know, if you're an analytical chemist and you just want to measure this analyte that's doing the fluorescing, it's pretty simple. The best place to excite is where this peak is. So we park our monochromator on this peak, and so that would be this monochromator here. So we select the best possible source light to feed to the molecule because it's the light that the molecule is most apt to absorb, causing that excitation. And then we park this monochromator at this peak emission wavelength because that's the light that the molecule is most likely to give up when it absorbs this particular wavelength. And you know, basically what we end up with is exciting at this wavelength and detecting at this wavelength, meaning that this monochromator is set for a different wavelength than this monochromator is. And that really contributes to this idea that the light from the source never makes it to the detector. So the light from the source is both going the wrong direction and is the wrong color to make it through the second monochromator and make it to the detector. And those two things added together make fluorescence what we call a zero background method. So zero background is an idealization, and essentially what it says is if there is no sample, if there is no analyte in the cuvette, you should see no light at the detector. And in those experiments that are presumably zero background, those things where you can actually count on there not being any signal at the detector unless there's analyte in the cuvette, you can typically turn everything in the system up. You can turn the source up to be very, very bright. You can turn the detector up to have a very high detectivity. Because zero magnified basically is zero, you can essentially turn things up until you start to have, you know, significant problems with the noise of the system. And as soon as an analyte shows up in the cuvette, you would get a signal that's in principle very large at the detector. So essentially, the reason that this is the reason that fluorescence spectroscopy is considered a very sensitive technique is zero background nature to it. And in fact, you might ask, how sensitive is it? There are experiments that have been done that have detected a single molecule sitting on a surface. So spectroscopy on a single molecule is now possible with fluorescence spectroscopy. There are a couple of tricks that you have to play. It has to be a microscopy, of course, because you have to be isolating one individual molecule in space. And the other thing is that molecule pretty much has to be on the surface because it can't be moving around while you're shining the light on it. So Essentially, this is a microscopy setup that allows you to detect a single photon, and those experiments have been done and are fairly interesting. Unfortunately, what I've just described is a fairly reasonable description of fluorescence spectroscopy and the strengths of fluorescence spectroscopy. It is not, however, the experiment that we're doing here. The experiment that we're doing here is fluorescence quenching. So, just realized that the titles on all of these slides are wrong. I think I'll go ahead with the wrong title on the top of these slides because the first title was right. The first title was right. So, you know, when you pick up on the fact that these titles at the top are wrong, hopefully that won't throw you too much for a loop. The fluorescence quenching experiment is a different experiment. In the fluorescence quenching experiment, what we're going to basically detect is the lack of the earlier thing that we just talked about, the lack of fluorescence. So how does that happen? Well, back to our physical chemist version of the diagram. This thing is referred to as a Jablonski diagram, by the way. It shows all the different states and all the different types of transitions that are allowed for those states. So here's our diagram that shows that ground state and that excited state of that molecule. Again, we labeled those S0 and S1. S in that context stood for singlet, which meant all the electrons in that molecule were paired up. And so we showed photons taking a molecule from the ground state to the excited state. We also drew on the other cartoon photons coming back down from the excited state to the ground state and producing a photon that we could detect in fluorescence. One last thing that can happen in this diagram that we didn't talk about on the earlier slide is that you can actually take molecules that are in this excited state, in this S1 state, and non-radiatively transfer them from that excited state, so that electronically excited state that we labeled S1, to some other electronically excited state. And in this case, we've labeled this state T1. So S stood for singlet. T, you can pretty well guess, stands for triplet. And the difference between a singlet state and a triplet state is that one of the electrons, or one set of electrons that used to be paired in the singlet state, is now unpaired in the triplet state. In other words, they're both spin up or spin down. And you think a little bit about that, it causes you a little bit of worry because the electrons that are in the same orbital have to be paired. But remember, when we promoted the molecule from the ground state to the excited state, we presumably took one of the electrons and put it in one of the other orbitals. And when you take the two paired electrons and place one of them in another orbital, then the two electrons don't have to be paired anymore. They can be paired, and that gives you the singlet state. They can be unpaired, that gives you the triplet state. One of the principles of electron pairing says that the triplet state is actually lower energy. I believe it's the Hund's rule. And essentially what it says is that this triplet state is actually downhill from the singlet state, so you can actually get to it from the singlet state without putting any energy into the system. Typically, to get that to happen, though, you have to actually have some kind of a collision. So I've drawn this line as a wiggly line, and what the wiggly line means is that there was not a photon transfer during this. This was a result of a collision between two molecules. This process, when it takes place, is referred to as quenching. This is one type of quenching. There are other types of quenching that can be, that are also described as quenching, other different physical phenomena that are described as quenching. This is one type of quenching where you take yourself from the singlet state to the triplet state, and the reason that this is described as quenching is the triplet state, because it's a triplet state and not a singlet state, is not allowed to generate a photon in returning to the singlet state. So this connection between the triplet state and the singlet state is forbidden, and that means that you don't get photons out of a system that undergoes this transition and then this transition. So this transition basically takes you into a dark state, a state that doesn't give you photons. So the terminology here is quenching, which means the amount of fluorescence goes down when this process happens. Okay, so where are our analytes in this system? Well, we already said the analytes, chloride and bromide, don't fluoresce. They're not the things that are doing the fluorescence. So we're not measuring those two things in fluorescence. What they do is they do the quenching. So they interact, chloride and bromide interact with the molecule that we sketched over here, the energy levels that we sketched over here, and take the molecule from its excited state into one of these non-radiative excited states, into one of these excited states that has a forbidden transition through these non-radiative type collision processes, and that results in less photons coming out of the system. So for the same amount of photons coming out of the source and going through the monochromator and hitting the sample in the cuvette, less photons are generated in this process when chloride and bromide are present, and therefore less photons make it through this monochromator and show up at the detector. So in principle, it looks like an absorption experiment. The more analyte you have, the more quenching you have. The more quenching you have, the less light you get, because the less of these connections you get. So the process basically means, or the overall physical phenomenon results in less photons coming out. Unfortunately, it doesn't follow the same equation as absorption does. So the equation that governs this process, or the equation that describes this process, I should say, is the Stern-Volmer equation. So this is the quenching equation, the Stern-Volmer equation. And what it says is that the F0, the fluorescence that you observe in the absence of a quencher, divided by F, which is the fluorescence you observe, the intensity you observe in the presence of a quencher, is equal to 1 plus KQ, the characteristic quenching relationship, characteristic quenching constant for that quencher, times the concentration of the quencher. This is a kind of a weird equation, so it helps to kind of think about the limits. If Q is equal to 0, if there is no quencher present, then the whole right-hand side, this KQ times Q term, goes to 0, and the whole right-hand side goes to 1, which means that F0 is equal to F, because that's what gives you 1 as a ratio, and therefore that's basically the definition of F0. That says the fluorescence in the absence of quencher is equal to F0. The other limit, when you start to increase the quencher concentration, is that KQ times Q starts to get larger. It basically is added to 1, and therefore the whole right-hand side of this equation gets larger than 1. And if you think about it, what must be going on, because F0 is fixed, is that if this right-hand side is getting bigger, the left-hand side has to be getting bigger. And if the left-hand side is getting bigger, it must be because F is getting smaller. So the fluorescence in the presence of the quencher is going down, which makes F0 over F go up, which means that it jives with the right-hand side of the equation. So there's a linear increase in this ratio as a function of concentration of the quencher. So that's the governing relationship here. So what that means is that we plot a whole bunch of points that have different quencher concentrations. We should get a line that starts at 1. The intercept should always be uniquely equal to 1.00, and you should get an increase in the quenching, which basically is registered through this F0 over F. So for every system, for every quencher concentration, you'll measure the F0 over F, and that is supposed to linearly vary with Q. So you're supposed to get a Y equals mx plus B. The B is supposed to be equal to 1. The M is supposed to be equal to this quenching constant. So one type of experiment that you'll have to do are these calibration experiments, and the calibration experiments are done with the quencher present and the analyte present, or in the fluorescer present. In all of the experiments, the fluorescer's concentration is constant, as is the light that's coming from the source, as is the wavelength that's being used on the monochromators, and the only thing that's varying during these calibration experiments is the concentration of the quencher. Okay, so that's a pretty good thumbnail sketch of what the experiment is all about. There's a complication, of course. There's a complication. The complication is that we have two analytes, chloride and bromide. And as we know, if you're going to measure two analytes, you actually have to have two pieces of information. You have to have two equations to describe a system where you can determine two analytes, two unknowns. And so to add an additional level of complexity to the fluorescence quenching experiment, we're going to determine two quenchers. And to do the two quenchers, we're going to have two different molecules, two different dye molecules. So the molecules that we'll use, the fluorescers, are quinine and acridine. So quinine and acridine are both pretty good molecular fluorescers. They both have these sets of energy levels that you can write out, including the possibility of quenching over onto this triplet state and not getting the light out. Obviously, the energy levels are different for the two different molecules, for quinine and acridine, which means that the emission and excitation wavelengths for quinine are going to be different from the emission and excitation wavelengths for acridine. So there's going to have to be a change of settings somewhere in this experiment. I'll say something about that pretty quick here. And you're also going to have two quenchers. So for each of the two dyes, for each of the two fluorescers, quinine and acridine, the effect of the two quenchers, chloride and bromide, is going to be different. So what you're going to end up with basically is 4 different calibration experiments, one with quinine and chloride, one with quinine and bromide, one with acridine and chloride, one with acridine and bromide. So you're actually going to create 4 different calibration experiments. Each of those calibration experiments is going to have a single dye and a single quencher, and you're going to plot the F naught over F for that particular dye, for that particular quencher. And again, very, very important that you realize that the intercept for this line should be equal to 1. If the intercept for this line is not equal to 1, something has gone wrong with your experiment. I'll talk in a slide or two about how we do the experiment, but we do sometimes run into problems. There are some things that go wrong with this system. So while you're taking the data, you should be working up the data. When you get to the end of the individual parts of the experiment, you take a look at your data and you make sure that the intercept in your calibration plots is equal to 1. If it's not, something went wrong. You really need to retake that data. Assuming that the calibration curve is linear and assuming that the intercept is 1, then the value of the slope, the number for the slope, becomes the quenching constant for that particular dye for that particular analyte. So, for example, if this was quinine, the fluorescence of quinine that was being measured and the concentration of chloride was being varied, note that we don't have any bromide in this system. This is a system that only has chloride in it. Then the slope of this line would be equal to the K for the quinine and the chloride. And keep in mind, this is important because at the end of the day, you're going to have to basically find out the unknown concentration of chloride and bromide in a system where you've measured both quinine and acridine, and therefore you can use the Ks that you derive from these calibration plots to calculate the unknown concentration of chloride and bromide through a solution of the simultaneous linear equations. So there are 4 sets of these calibration plots. All of the calibration plots should extrapolate back to 1. They should all be reasonably linear. If all of that is true, in the end of the experiment, you will be able to measure the unknowns and derive the chloride and bromide concentration in the liquid phase, and then work your way back to the solid phase challenge sample that we started with. Okay, so that's, again, sort of all the details of the experiment. Making it work, there are a couple of other things that we need to consider, and I see that my labels didn't do a very good job of maintaining themselves here. This is supposed to be an F naught, and this is an F. This is an F naught, and an F, and an F naught, so on and so forth. So as I talk my way through this, I'll point that out again. So here are some details on how you can actually make this experiment work better. So the first thing that's very important is that quinine and acridine take different wavelengths. So the excitation wavelength, the in monochromator, and the emission wavelength, the out monochromator, the one between the source and the sample, the one between the sample and the detector, those are different for quinine and acridine, and they're given in the lab write-up, so it's not like you'll have to find them or anything, but you do have to change. And when you change the wavelengths on this fluorometer, you never will actually get back to the original condition. So your measurements have to be taken, all of your measurements have to be taken with one dye. So you have to measure all of the unknowns and knowns for one dye, and then you need to switch over and do all the measurements for the other dye. My advice is do all the measurements for one dye, work up the data the way I just described it, and make sure the data makes sense. Make sure the intercept is 1, make sure the plot looks relatively linear, and make sure that the unknowns are on your calibration plot. If that's not true, this experiment isn't going to work. And it makes sense to go through and remeasure measurements before you change the wavelengths rather than after you change the wavelengths, because once you change the wavelengths, you're going to have to come back and measure the entire set. So maybe you can realize that one of the points didn't make sense, go back and measure one individual sample. So one more thing I will point out as we're going along is that all of these samples look the same. Quinine and acridine have different spectral characteristics in the UV. So in other words, the excitation wavelengths are different and the emission wavelengths are different, but they don't absorb in the visible, and so they're all going to look like clear solutions to you. So it's really important that you keep all of the individual samples straight. So make sure you label all of the volumetric flasks that you're using. Make sure you're very careful about knowing which sample you're working with when you're doing the actual experiments. Work your way through all the quinine samples, move the quinine samples, do the calculations, make sure the quinine samples make sense, move all the quinine samples out of the way, bring in all the acridine samples, change the wavelength readings, and do the whole thing again. So if you do that, you have a reasonable chance of success. Even within that, though, there's another trick that we suggest, and the one other trick that we suggest is the actual stability of the instrument is not that great. In other words, if you had to measure these F and F naughts over the course of a day, you would have trouble. But in fact, what you have to measure is the F and F naught of a sample with a different quencher in it, but the F naught sort of can always be measured. So what we suggest is that you have 3 cuvettes that you actually use in this experiment. One of them contains the blank and always contains the blank. One of them contains unquenched dye, so for all the quinine experiments it'll be the same solution in the same cuvette, and the other one contains the dye plus the selected quencher concentration, or including the unknown, possibility of having the unknown in there. So so basically blank, dye plus quencher, and that means that this is a measurement of F naught and this is a measurement of F. The blank you typically only have to do every once in a while, so you throw the blank in there and make sure that you're getting a 0 on the instrument. That happens once every 10 samples or something like that. Every time you measure one of these F, every time you measure one of these quenching concentrations, you will follow the following sequence, or at least we recommend you follow the following sequence. So measure the unquenched dye, the F naught, and then measure the dye with the quencher, and then measure the unquenched dye, and then measure the quenched dye, and then measure the unquenched dye. So why are we doing all of this? Well, every time you measure the F naught and measure an F and come back to the F naught, those 2 F naughts should be about the same value. So it's a good way to keep track of whether the system is drifting. If the system is drifting, measure the entire set again. Once the system stabilizes to the point where the F naughts are roughly constant, they're just moving around a little bit due to noise, then you're going to get a good measurement of F naught and F. While the system is drifting, you will never get a good measurement of F naught and F, even if you averaged, for instance, these 2 F naughts and averaged these 2 Fs. So wait until the system is at a constant level. And really the key to this is getting in. If you're the first group in the morning, get in, turn the instrument on, and let it warm up, because it takes about an hour for it to warm up to a good level to where you'll actually get good data out of this instrument. If you're in the afternoon, quite likely the morning lab will have turned it on and you won't have to wait that long for it to warm up. Just make sure whenever you, as soon as you walk in the door for the lab, make sure that the lamp power supply is on and that the lamp is warming up and that the rest of the system is on. In other words, the cooling fan on the spectrometer is running. And that the system is warming up and getting ready for you to do the experiments, or is already warmed up. Either way. Okay, so the reason for measuring the F naughts on either side of the F is that you can check for drift and make sure that the drift is not occurring, make sure that your value of F is constant, make sure that your value of F naught is constant. But if you're going to measure on either side and you think about it and you'd like to measure 2 values of F to get an average value of F, then why not put one more F naught on the other side? So what you've done is you've bracketed 2 sets of Fs with F naughts, and to get the actual answer, you would take the average of this F naught, and this F naught for the F naught, the average of this F and this F for the F, and therefore your overall F naught over F is an average of several points, which makes it a lot more certain. And the other thing that you can do is you can take the 3 different values of F naught here and calculate a standard deviation for F naught, which is a pretty good surrogate for the uncertainty or the standard deviation, the relative precision of the fluorescence measurement itself. And so when you go to actually calculate the unknowns in the system, it'll be useful to have that standard deviation for the F naughts. There are 2 different standard deviations that you can calculate here. You can calculate the standard deviation within a set. You can also calculate the standard deviation for all of your samples. The one is sort of an overall long-term uncertainty or long-term drift of the system. The more applicable one for the calculation that we'll be doing here are these F naught within a single set of 5. One last caveat about these cuvettes. Most cuvettes are not exactly symmetrical, and so always be sure that you're always putting cuvettes in the same way into the fluorometer every single time. And that holds for every spectrophotometer that you ever use. If you go flipping the cuvettes around either back to front or side to side, doing right 90-degree turns on them or 180-degree turns on them, you're going to always get weird uncertainties in the answer. So make sure that your cuvettes always go into the spectrophotometers the same way all the time. And if that means making a little black mark on the top, so be it. Just make sure that you keep that straight. Okay, so you've done the sequence of F naughts and F's. You've determined both F's of F naught. You've determined F naught over F for that particular quencher. You use that data to calculate all of those Ks. So there are sets of, basically there's 4 individual Ks for a combination of a dye, quinine, and a quencher, chloride. And once you have all of that calibration data, once you have all of those Ks from those individual plots, and you've measured the unknown F naught and F for the 2 dyes, for the quinine and acridine, you can sit down with a sharp pencil and figure out how to calculate the concentration of chloride and bromide for this system. And it's very similar to the pH experiment we did earlier in the lab. Basically what you're going to have to do is either do some kind of a substitution, make one equation, cancel out one of the unknowns from one equation and substitute back into the other equation, or some kind of a matrix solution. In either case, what you're going to end up with for the answers are the concentration of chloride and bromide for the 2 challenge samples, for the 2 concentrations of challenge samples, and then work your way back to the concentration or the composition of the solid. And then the harder part is to figure out the uncertainties associated with those concentrations that you calculate. So calculating concentrations, a little mathematically challenging, more mathematically challenging, propagating the errors associated with all of those numbers back into the answer that you've got, which is the chloride and the bromide concentration. So if you think about it, there are a number of different sources of error. We'll assume that 1 is 1 and that therefore that there's no source of error in 1. But F naught over F for each of the unknown samples is subject to some error. So when you measure the unknowns, you'll get a value of the S of F naught for the F naught value. I would recommend that you assume that same value of S for the S. And so there's actually 2 contributors to the uncertainty in the F naught over F. There's the uncertainty in F naught. There's the uncertainty in F. There are 2 sets of those that you need to calculate uncertainties for. There are also uncertainties associated with all 4 of these slopes. So these are all slopes. You remember that we can use the calculations within the data analysis tool pack of Excel to calculate the uncertainty associated with these slopes. So the standard error associated with the slope is S sub m. So you should be able to get all of those. If you don't know what I'm talking about there, I would recommend that you go and watch the spectrophotometric determination of iron presentation, because it talks in some detail about how you get those statistics, how you get the S sub m's and limits of detection and things of that nature. So basically you've got essentially 6 contributions to the error. So we've got an error in F naught over F, we've got an error in F naught over F for the other dye, and we've got errors in all 4 of these values of K. All of those errors have to be propagated through to the final answers for chloride and bromide. And it's a fairly long discussion of how you would do that. So rather than doing that, I'm going to refer you to either to Skoog, Westholler, and Crouch, the old white book that we used in quantitative analysis. And in that case, it's chapter 6 that talks about propagation of errors. And again, that chapter was ported into an appendix at the back of Skoog, Holler, and Neiman, the instrumental book that we're using. And so there's a similar section on propagation of errors there. I will point out that there are both types of propagations here. There are things where you're adding 2 numbers together, and there are things where you're multiplying 2 numbers together, and those have separate rules about the variances. So variances add or relative variances add. In principle, you have to keep track of those different ways of treating numbers in order to get the final answer for the uncertainty on the chloride and the bromide. So getting the answer in this case takes a little bit of work mathematically. Getting the uncertainties associated with the answer takes quite a bit more work. We're sort of expecting that you will do all that work, but we highly recommend that you do that work during the lab session while you've got the help of the TA and the other people in your group. So when you walk out the door, hopefully you have already gotten all of the plots built, and you know the answer for chloride and bromide, and you know the uncertainties associated with that answer. And then all you have to do is describe how you got all of those things in the lab write-up. So that's essentially all that I had. When you're doing this report, one of the nice things that you can do is when you build these plots, which are the quenching plots for the individual quenchers, a lot of times you can put two of those plots together on the same plot, and that allows you to either compare the quenching of, let's say, chloride for the two different dyes, or the quenching of chloride versus bromide for a given dye. And in either case, it's kind of a compelling figure because it shows that different quenchers have different effects on different dyes. And of course, that has to be true in order for this experiment to work. So it's a nice thing to point out. And then basically the only other thing that ever goes wrong with this experiment is that people get the colorless solutions mixed up. And so again, if you work up the data at the end of each set, at the end of the acridine set and at the end of the quinine set, a lot of times you'll pick up on the fact that your calibration curve doesn't make sense, and going back in and measuring one or two samples is a whole heck of a lot easier than coming back and measuring all of the quinine set again, or all of the acridine set again, or worst case, that you've thrown out all the solution samples before you discovered this error and you have to reconstruct the entire calibration set. So words to the wise, work up your data as you go along, make sure the data makes sense in sort of as each data point is derived. Make sure the data in aggregate makes sense before you walk out the door, because this is a hard enough lab to write up when the data looks good. It's next to impossible to write up when the data looks bad. Okay, so I will stop there, and thank you for your attention.